a new virtual speaker series featuring content that we hope you will find fascinating and inspiring. This new program is designed for those who are simply interested and curious about science, for those who work in the scientific arena, and for those who are committed to supporting science education. We believe there is something here for everyone. I'm Chris Brent, and I've been an active member of the Northern California chapter of ARCS Foundation for 23 years. In fact, I'm a second-generation ARCS member, joining and sharing my mom's commitment and passion for the ARCS mission. Recently, I served as president of my chapter, and I continue to be enthusiastically engaged in leadership roles, both in the chapter and at ARCS National. On behalf of the ARCS Forward Committee, thank you for joining us today. We're very excited to be launching ARCS Forward. The name of this series is derived from a desire to move our organization forward and to build and renew relationships in support of science and a better future for us all. As a bit of logistics, I do want to let everyone know that this event is being recorded. And now, while some of you may be very familiar with ARCS, others may be wondering, what is ARCS? Well, ARCS stands for Achievement Rewards for College Scientists. ARCS Foundation is comprised of 15 chapters around the country, with a singular mission to advance science and technology in the United States by providing financial awards to academically outstanding US citizens studying to complete degrees in science, technology, engineering, and medical research. As a nonprofit foundation committed to science education, ARCS is unique in three important ways. 100% of the ARCS award funds go directly to scholars. The awards are 100% flexible and unrestricted. And we are a volunteer organization of women 100% dedicated to the next generation of scientific discovery and innovation. For these reasons, ARCS Foundation is considered to be a model for science educational philanthropy. And just as a bit of history, ARCS Foundation was founded in 1958 in response to the launch of Sputnik by the Soviet Union the year prior. A group of intrepid women in Los Angeles decided that the best way to ensure leadership in science and technology would be to invest in the education of young scientists. Now, 63 years later, ARCS Foundation is proud to have provided more than 10,000 scholars with awards totaling more than $120 million. Now, ARCS Forward is a brand new initiative. The goals are to, 1, reconnect with ARCS alumni, 2, enable young scientists to virtually meet and network, and 3, facilitate a connection between ARCS members and others who appreciate and value the impact of science. I'd now like to introduce Nancy Chambers, who will lead this first session. Nancy is an officer and director of ARCS Foundation's National Board, where she serves as board secretary and is a member of the executive committee. Nancy is a 14-year member of the Atlanta chapter, and there is no one better to talk about the ARCS Alumni Hall of Fame and to introduce our most recent inductee than Nancy. She is the architect of the Hall of Fame, which launched with our first inductee in 2015. Welcome, Nancy.
Thank you, Chris. And I'm happy to tell you a little bit about the ARCS Alumni Hall of Fame before I introduce our special guest today. Members of the ARCS Alumni Hall of Fame are ARCS Scholar alumni who have made outstanding contributions to the advancement of science and to increase our nation's scientific competitiveness. Nominations are made by ARCS chapters, members, scholars, and academic partners. Selection is by a panel appointed by the national president and is based on 5 categories of alumni contributions in the areas of scientific innovation, discovery, economic impact, development of future scientists, and enhancements of U.S. scientific competitiveness. The ARCS Alumni Hall of Fame was established 7 years ago to bring national attention to the impact of ARCS scholars on science and to honor the best of the best of the best who have made discoveries and innovations that change the way we live. There's no better illustration of the importance of the ARCS mission than the accomplishments of its scholars' achievements. For example, ARCS Hall of Fame members include Dr. David Mangelsdorf, whose research on orphan receptors launched an entire field of biology and has changed the way we treat disease. Dr. Lichten, whose contributions to GPS technology are used to ensure reliability in today's commercial aircraft, and Dr. Jessica Meir, who made the first all-female walk in space that has inspired women to careers in STEM. These are just a few examples of the amazing work that ARCS scholars contribute to society. Today, it is my extreme honor to introduce the 12th inductee into the ARCS Alumni Hall of Fame, Dr. F Peter Schlerb, who is recognized for his leadership and vision for the concept, design, and construction of the large millimeter telescope Alfonso Serrano that was instrumental in the capture of the first image of a black hole, which confirmed Einstein's theory of general relativity. Dr. Schlerb is a planetary scientist who specializes in radio astronomy. He was also a key collaborator on the Rosetta spacecraft that made history in 2016 when it became the first to orbit a comet and land on a comet's nucleus. Dr. Schloerb was an ARCS scholar in 1977 at California Institute of Technology, where he received his PhD in planetary science. He is currently a professor at University of Massachusetts Amherst, director of the Five College Radio Astronomy Observatory, and director for UMass participation in the Large Millimeter Telescope Alfonso Serrano. On April 10, 2019, scientists revealed the first picture of a black hole. This achievement was an amazing international collaboration of hundreds of scientists around the world and was taken by the Event Horizon Telescope, one of which, and arguably the most significant, is Schlerb's Large Millimeter Telescope. The largest steerable single dish radio telescope in the world at 50 meters across, the Large Millimeter Telescope is the length of an Olympic swimming pool and the result of a multi-year effort that began in 1994. At a cost of $180 million, the LMT was developed as a joint project between University of Massachusetts and Mexico and is located atop Sierra Negra at an elevation of 4,600 meters in the state of Puebla, Mexico. It's a part of the worldwide Event Horizon Telescope, which links 8 telescopes around the globe to form an Earth-sized virtual telescope with unprecedented sensitivity and resolution. It offers scientists a new way to study objects in the universe predicted by Einstein's relativity theory. Dr. Schlerb has received many honors in his career, including having an asteroid named after him, which he says is no big deal. He says lots of people have asteroids. But his most notable recognition came this past year when the Event Horizon Telescope team received the 2020 Breakthrough Prize in Fundamental Physics, which is awarded to the world's top scientists working in the fundamental sciences. This prize recognizes the advances that have changed human thinking through great discoveries. The Event Horizon Telescope received this prize for watching the invisible and producing the first ever image of a supermassive black hole. In speaking about this accomplishment, one of Dr. Schlerb's colleagues at UMass said, "In this feat of human ingenuity, perseverance, and scientific vision, the Large Millimeter Telescope has played a key role. Pete Schlerb deserves credit for overseeing much of the conception, design, and construction of the LMT. Through selfless dedication, he has enabled an international experiment that has produced what has been called, quote, the image of the century." It's achievements like those of Dr. Schlerb that validate the ARCS mission and remind us how important it is that ARCS continues in decades to come. Dr. Schlerb's accomplishments are truly advancing science in America and the world, and it is my pleasure to introduce him to those attending this first ARCS Forward presentation today. Dr. Schlerb.
Well, thank you, Nancy, for those nice words. I always, I've had the opportunity to talk to Nancy and read bios she's written about me and so on. And I always joke that basically what we'd like, I'd really like Nancy to speak at my funeral because she always does such a great job of talking about me and my modest accomplishments. But seriously, one of the things I'd like to do especially is to acknowledge to the ARCS members how much I really appreciate this award and this honor. It means a great deal to me, as does the ARCS Foundation, because the support of the ARCS Foundation when I was a graduate student was important for me in my development as a scientist, as I'm sure it is for all of the other ARCS fellows. And I just want to thank the foundation members who are on the call today and acknowledge that because the support of graduate education is so important to the advancement of science in the United States.
Well, thank you for those words and for being here to talk with us today. Your telescope is the first of its kind and a significant component in the Event Horizon Telescope. Tell us what makes it unique and how you had the vision for its design.
Okay, so the thing that you have to realize about telescopes is that unique is a very loaded word, because every telescope on Earth, if you ask the people that use it and build it, they'll tell you that their telescope is a unique telescope. So let me explain that my telescope is a unique telescope for a couple of reasons. I mean, first of all, it is the biggest of its kind in the world, but in order to really state that, you have to be very careful about how you define biggest of its kind. So technically, 50-meter fully steerable antenna, biggest of its kind for wavelengths, very short millimeter wavelengths, wavelengths like, in the sort of range of 1 to 3 millimeters or so. But that said, I think one of the things that makes our telescope really unique and special and is its design. Because when we conceived the telescope in the 1990s, we took a chance. The telescope is designed to have a big reflecting surface. That 50-meter diameter reflecting surface is actually under the control of computers. We have 180 surface panels there, each of which is under the computer control. People had talked about it, but nobody ever built a telescope with an active surface like that where the active surface absolutely had to work in order for the telescope to achieve its scientific objectives. And so I'm very proud of the fact that we took that that step and built that telescope and have it working today.
So what was the biggest challenge in the construction of something this unique?
So, you know, it would be fun to talk about technical challenges, but what I'd like to do is to tell you that I think the biggest challenge was not a technical challenge. As you mentioned, the telescope is built as a collaboration between the University of Massachusetts, Amherst, and the country of Mexico. So what we had was a project, an international project between two countries. Actually, former President Zedillo once when I met with him once said to me, well, you know, I always thought that this was, you know, quite an ambitious project for, you know, a moderate sized state university to do a collaboration with an entire country. But I can tell you that international projects of this sort are among the most difficult to pull off. And we're seeing that as telescopes and scientific projects get bigger and bigger and more international. You spend an awful lot of time working on those international relationships and trying to manage the project. And that's really where I would say, that's really, I think, was the biggest challenge. The technical things kind of come along. The relationships and what you learn by doing international projects are things that really have to consume a lot of your attention, and you have to put the effort into making the project work.
So why Mexico? Why the specific location within Mexico? How important were physical factors in the?
Well, okay, yes. People ask me, you know, why is the telescope built in Mexico? And the short answer is because they came up with most of the money. So everybody's nodding. Okay. So but then of course, you know, we had to pick a site for the telescope that was actually a good site for doing the kind of astronomy that we wanted to do. And so we and our Mexican partners spent an awful lot of time surveying possible mountaintop sites in Mexico. Why mountains? Because basically the important thing for millimeter wave astronomy is to get above most of the water vapor in the atmosphere. That's why we're at 4,600 meters elevation, or about 15,000 feet elevation on top of this extinct volcano that you saw the pictures of in Nancy's presentation. We get above most of the water vapor in the atmosphere. Actually, a lot of oxygen as well, which is also a good thing, because it turns out at some millimeter wavelengths, oxygen actually interferes with the signal. So the reason is to get above that, and we had to find a great site. We built site test equipment and stuff and placed it on mountains all over Mexico. I have a million stories about that, but in any case, in the end, we wound up in this spot, and it's a great spot. It's a 2-hour drive from our sister institute to the top of the mountain. So it makes it quite accessible for us to make use of the telescope.
So let's switch gears a little bit, and I ask you to tell us about the Event Horizon Telescope and the international collaboration that you were involved in.
So this concept of the Event Horizon Telescope is something that was many years in the making. There are a couple of people that I could cite as being sort of there are probably lots of people that would claim to be the intellectual leader of this whole thing, but there are a couple of people I ought to particularly cite. One is Shepard Dolman in the United States, and the other is Heino Falke in Germany. They both realized, I think individually at first, that we could, using the technique of very long baseline interferometry, where, as Nancy said, we use telescopes spread out all over the world to simulate, or to basically act as one big giant telescope with enormous resolving power. It was realized that if you could construct such a thing and make it operate at a wavelength of 1 millimeter, then you would be able to resolve, take a picture of the closest supermassive black hole to us, which is the one at the center of our own galaxy, the Milky Way. And we could also resolve some really big, really supermassive black holes at more distant, in more distant galaxies, and that's the one in the galaxy we call M87 that was resolved for the image. So these guys had recognized this potential, but then you got to do it. You got to organize telescopes all over the world and get people excited about the project and come up with the developments that are necessary in the instruments and so on to in order to carry out the experiment. For example, at our telescope, we didn't have a 1 millimeter receiver when we first were talking to them, and so my friend Shep Dolman went out and basically helped us to raise the money to build the 1 millimeter receiver that was essential to have the LMT as a part of the experiment. But it took years of meetings and workshops and getting together. I mean, going from the time that before the time that the LMT was really completed, until finally the observations were made. And I would go to those workshops, and in part because we were being pursued at some level for our big telescope, and I realized this was going to be really important for us to try to do, and so my colleagues and I, by golly, we got involved and we did it. So that's.
How many scientists were involved in that collaboration?
There are something like 300 on the breakthrough prize. There were something like 340 people representing, I don't know, maybe 30 countries. I used to have these numbers in my head, but it's an enormous collaboration. At least, but these days in astronomy, lots of collaborations get big, and of course, in some other areas of science, it takes pages of the journal to contain all the co-authors for the papers. So it's quite a big undertaking. It's very international. I mean, people from all the countries, sort of major scientific countries in the world, participating. The United States has taken leadership in a number of in funding a number of things, activities for the Event Horizon Telescope, including helping us at the LMT with funding.
So the data for your black hole image, it was captured in 2017, but the image wasn't published until 2019. What took you so long?
So this is a little bit like asking graduate students, why is their thesis taking so long? But the fact is that there was an enormous amount of work involved. So I just want, and it's complicated work. So I'm going to recite a couple of facts to you. So first of all, the total amount of data collected for that experiment was measured in petabytes. So a petabyte is a million gigabytes, right? So it's a big number, right? And so the process of producing the final image amounted to going from petabytes to kilobytes, because basically the picture of the black hole you saw, it can be represented in one of these standard images in about 40 kilobytes. So that's a factor of 10 to the 12th power reduction in the data to finally get the final image. So a factor of 10 to the 12, you know, a 1 with 12 zeros behind it. That's a pretty big factor. And so you might appreciate that it takes some time to accomplish that. Moreover, in the work, we wanted to be sure that you know, there was no sort of self-deception going on when you're reducing the data. So in fact, the image that is published was produced, you know, was first produced by 4 teams working independently to produce the image. So each group got the data, worked to produce the image, and then when they were all done, they got together in a room and put their images up on the screen and saw, oh gosh, we all see the same thing. And so then at that point, that gave a great deal of confidence to the result. Because as I say, this business is pretty tricky, you have to be careful with these reductions, and the fact that 4 different groups all came up with the same result meant that it gave us a lot of confidence that the thing was real. And so the final image is actually kind of an average of those 4 independent groups' work, and so I mean that's that. It sometimes it takes a while.
What did you think when you saw the image the first time?
Well, you know, I think you know, one of the remarkable things about the first image was that it's kind of exactly what you would have thought it would look like. So, you know, there have been, you know, attempts to, you know, draw figures and so on of what would a black hole look like if you were looking at it and stuff. And you've probably seen these things in like the movies, like years and years ago, there was the movie about the black hole, and then more recently, the movie called Interstellar. And, you know, those pictures of what would a black hole look like were based on what theoreticians told artists. And so we had some idea what you might see, and, you know, by golly, there it was, right? So, I mean, it's sometimes it's kind of surprising, you know, that something that hasn't been seen before turns out to look basically like what you might have expected it to look like.
So why do you think people are so interested in black holes? They don't affect our everyday lives. What is so fascinating about them?
Okay, so I'll tell you a story. After the discovery, or after the announcement of the discovery, which was pretty neat, you know, big coordinated unveiling of the image all over the earth, you know, with groups in Europe, and we went to the meeting in Washington, and our colleagues in Mexico had their own thing, and it was quite an event, and it got quite a lot of coverage in the press. You know, some of my colleagues in the Event Horizon Telescope think that billions of people have seen that image, and that image is going into the Museum of Modern Art as one of the iconic images of science. And it will be hung next to the famous Apollo 8 picture of the Earth rising over the limb of the moon. So what a lot of hoopla, let's say. I was curious myself about your question, Nancy. So basically I teach a course where, you know, we take a topic and we study it. And I said, I laid down the topic of the semester. I said, okay, we did all of this, we got all of this excitement, why? And so we spent the term talking about black holes and why were people interested in them. And it's really quite amazing, you know, that black holes have somehow, you know, gotten to be a part of our culture. I mean, there's songs about them, there's movies, there's, books. Not only, I mean, my shelf I've got now lined with, because of having to teach this course, I've got lined with 6 or 7 books entitled Black Holes, Eat the Universe or something, I don't know. But and then scientifically they're very interesting. They touch Einstein and all the rest of that stuff. I think that the culture was sort of geared up to with automatic interest, let's say, and as you say, they don't affect our everyday lives, and I think in a way that's why why maybe people could look at that picture and say, oh, those astronomers made this picture of the black hole, and not really worry too much about exactly how it got made, because I'm telling you that the process to actually create the final picture is a complicated process that takes a lot of explaining. I mean, I think I could explain it to everybody, but it would take us a couple of hours, and believe maybe you don't want to hear that lecture. But the point is that it's an example of a scientific result that I think was interesting because it was just accepted by people. Nobody said, "Oh, I don't believe those scientists, saw this black hole." I mean, maybe somebody did, but nobody says, "Oh, I don't believe in the science." People say, people are interested in the science. People accept what scientists say in general. And I think it's important, particularly for the development of science in the United States, that we try to keep science as an important and respected field, and we do everything we can to maintain that trust relationship, which I think that in general scientists have with the public.
So what's next for you and the LMT?
So just this last year, the National Science Foundation gave us a nice grant, which will allow us to open up the LMT to any American astronomer. Right now, before this time, the University of Massachusetts, having put something like $60 million into this project, has been, is basically the beneficiary of all of our effort. But now, because of support from the National Science Foundation to help us support the operation of the telescope, we're going to be able to allow a portion of the time on the telescope to be used by any American astronomer. And I think this is going to be a great thing for the telescope and also for the U.S. astronomical community. And so one of the things I like about it is that it's going to give us the money we need to really kind of upgrade the operation of the telescope from a situation where a few of us experts can go down and we know all of the buttons to push and stuff. It's going to upgrade it to the point where any astronomer will be able to write a proposal, describe a project they'd like to do, and through peer review competition, be assigned time and the ability to go ahead and get the data that they'd like to do for their science.
Well, thank you, Dr. Schlerb. This was just a fascinating discussion, and hearing about your research, the collaboration, the Alfonso Serrano telescope. And I love the fact that the picture will be in the Museum of Modern Art. That's taking STEM and making it really, truly STEAM with the arts included. So thank you for that. Your work is really fascinating. What an impressive career you've had. We do have many questions that came in through the chat. So we're just going to pick a couple. And the first from our ARCS National President, Sherry Lendine. How often do you travel to your partner institute in Mexico?
Well, hi, Sherry. And the answer used to be quite a lot, but for the last year or so, not at all. One of the things that we've all discovered with Zoom, I mean, we used to do Zoom meetings before Zoom meetings were, like the thing, right? Now we do still spend quite a lot of time talking to each other and trying to make our plans and so on. But before that, I mean, there were years when I would go for, a few days a month in order to sit down with people and talk about what's going on. That's the kind of communication that you have to have in international projects. There's no substitute for having relationships with your counterparts in the project. So for a while there, I think I was adding up to something like 25% of my time spent in Mexico, usually looking up and down the hall, trying to find Alfonso Serrano, for whom the telescope is now named, to track down one thing or another.
Well, thank you for that. And it's hard to pick the questions. And I want you to know I'm not going to be on the hot seat. People are feeding me which ones to ask. So the next is from Wendy Lynn. What other objects do you anticipate to capture in the future in addition to that magnificent image of the black hole?
Well, okay. So for the Event Horizon Telescope, hold on to your hats, because we also collected a lot of data on the galactic center, the supermassive black hole at the center of our own galaxy. And eventually those results are going to be released. I'm forbidden for saying any more than that. But that's going to be pretty neat. The other thing is that, when we designed the telescope, the thing that I call the killer app for the telescope is actually not about black holes and very long baseline interferometry. It's actually for the fact that in our particular wavelength band between about 1 and 3 millimeters, it turns out that the universe conspires to have a really kind of unusual behavior. Usually, when you teach astronomy, you have to teach the students that the farther away something is, the fainter it gets, right? So and you talk about how it goes as 1 over the distance squared. And that's true. If you look out into the universe, the farther away you look, the fainter and fainter objects get, until at some point in the very distant universe, the fact that because the universe is expanding, the farther away you get, the more the light is shifted to longer and longer wavelengths. What that does is that at 1 millimeter wavelength, the light from the place where galaxies emit the most light, that wavelength, which is like 100 microns, actually gets shifted into the millimeter band where we can see it. So so if you look at these distant objects, as you go farther and farther away, they're fainter and fainter, and then all of a sudden they stop getting fainter. So you can, once you hit a particular threshold, which we hit, you can see everything out to the formation of the first galaxies. And that is the killer app. And that's what has generated, I think, most of the excitement in millimeter astronomy in these days. Although maybe when David talks later, I'll be more interested in following up gravitational wave events or something. But now me, I'm a planetary scientist. So the things I like are comets, actually. And I've had only one opportunity so far to observe a comet with the LMT, but it could be potentially spectacular. We try to learn about the composition of comets by studying the gases that they emit from their nucleus. And we can do that with a big telescope like the LMT.
Wow. Well, we have time for just one more. And so this is eeny, meeny, miny, mo, but from Janelle Monet, wouldn't you say that this black hole conformation tells us more about the history of different solar systems within the universe? Would that be true?
So remember, solar systems, that's basically planets around stars, right? And in the case where we're looking at supermassive black holes, the we're looking at objects that formed at the center of an entire galaxy. So we're here in our solar system, right? You know, one tiny little, you know, speck of dust and a huge galaxy of, you know, then when we look out, we get to see the all of the other galaxies appear to have black holes like the one we saw in them. And there have been, through the years, theories built up, basically since the origin of radio astronomy, theories built up about you know, what's going on in distant galaxies that's causing them to be so bright, particularly at some radio wavelengths and so on. And you know, what is it that we're seeing out there? And all of the theories pointed to made use of a black hole at the center of the galaxy. But of course, those were theories and ideas, right? Once you've actually seen that this thing is reliably a black hole, then you know, then maybe that makes you feel better about the whole things. Although I have to say that you know, astronomers had no doubt that was there.
Thank you. I appreciate that. I am in no way anything in the stars. I'm like a biologist. So, but I have a friend who's like an astrophysicist, and we're both getting our PhDs together. And just some of the things you were talking about, I'm like, oh, this is what she was like explaining to me. So I just got very excited. So thank you for explaining that to me. That's super exciting. There's a lot more going on out there beyond what we think of our everyday, but it's so cool. So thank you for being here and sharing this with us.
Well, sure.
Wonderful, and thank you for jumping in there. That's wonderful. These were great questions, and there are many more out there, and you've got a real fan club now, I think, Dr. S. So thank you. I want to also give my thanks to Nancy Chambers for the great job in moderating that portion. And so now, boy, what a great opportunity to hear firsthand really about your research and all of those discoveries that you have made in the far reaches of space and continue to make. And we are really, truly honored, Dr. Schlerb, by your association with ARCS since receiving the ARCS Scholar Award in 1977, and that you still list ARCS on your CV as an important academic and professional honor. And being an ARCS Scholar is truly for life, and ARCS Scholars are truly a community of excellence, with many actively mentoring and encouraging the next generation of scientists. And speaking of the next generation, I'd like to introduce a current 2020-21 ARCS Scholar, Dave Coulter. Dave is a PhD candidate at the University of California, Santa Cruz, and is an NSF Graduate Research Fellow. His research in the Department of Astronomy and Astrophysics centers on finding and understanding the electromagnetic radiation associated with gravitational wave events. And he and his team were the first to locate such a source. This earned them the distinction of Breakthrough of the Year 2017 from the journal Science. So welcome, Dave, and thank you for being here. And I'm sure you have many questions you'd like to ask Dr. Schlerb. How about starting with one and then taking us through a little bit of your background and the work that you're doing?
Sure, and thanks for having me. Thanks for this opportunity to be here. Dr. Schlerb, as a young astronomer, and you've gone through my process of going to grad school and trying to get into the field, what is that piece of advice that maybe you wish you'd received, in my position? I'm interested to hear what you have to say about that.
Okay, well, I'll try to keep this short because I'm interested in hearing what Dave has to say. I actually did receive this piece of advice. I was once very worried about my future, and I went to my thesis advisor at Caltech, and I said, gee, I'm very worried about, am I going to be able to get a job and blah, blah, blah. And he said, oh, that's no problem. Just be the best at whatever you do, and you'll have no trouble finding work. And I thought about that, and I was actually a little bit depressed by that answer, to be honest. But then I realized that really what that was about was encouraging me to follow the things that I was interested in, follow my own loves and research and so on, and not worry too much about the rest of it, and that then things would come. So my advice is just do what you love, and you won't have to worry.
Thank you. I think that's good advice. And I'm trying to take that to heart now as well. So, so a little bit about myself. I thought I would give a little introduction just because it's been a long and winding road for me to get here. I'm a little bit of a late bloomer when it comes to science. Originally, I got my degree in history and political science, actually, a Bachelor of Arts. And after that experience, I ended up just kind of bouncing around a lot of office jobs, and I couldn't really find good serious work until I landed this job at the VA Medical Center of all places as a medical records biller, believe it or not. And so this is my auspicious start as an astronomer. After putting medical records into the computer for so long, I was sort of face melting, and I thought there's got to be a different way to do this. And then I discovered this concept called scripting, which is like rudimentary programming, right? So I programmed my job into the computer system, and I think I was the only employee ever to get essentially a reprimand from the federal government for installing software on federal computers, but at the same time an employee of the month award for tripling my prescription billing. So, but that kind of set me up to start thinking about how I had this power over my future if I just sat there and thought about it and executed, right? So, I got into programming at that point. And I did what any Bachelor of Arts would do when they want to learn programming. They buy a book, and I couldn't afford a computer, so I ended up writing on my computer programs on a notepad, just trying to visualize what they would do. And around 2008, I was able to parlay that into a software development job. Believe it or not, this is before the whole market crashed, and I was able to get into a small development team and start learning programming. And that's how I bootstrapped myself into science. By doing those programming jobs, I was able to go to community college at night. I was able to eventually build up my coursework. And then I did a NASA internship actually at Wallops Flight Facility in Virginia. And so there, it wasn't astronomy, but they said, hey, we have a research position for you. You can program so you can solve problems. Would you like to do this? And I said, I'll wash dishes at NASA. So I went to Virginia. I worked in a hangar around a whole bunch of NASA helicopters and airplanes, for measuring sea ice and things like that, and wrote genetic programming to understand ocean ecosystems. Was able to parlay that into a summer job at NASA JPL. And actually, I saw your CV, Dr. Schlerb, that you did some work on Saturn, and so I did some work on Saturn in the infrared at JPL, and then eventually made my way to Goddard Space Flight Center, wrote my first paper on populations of stars within galaxies and how you can sort of trace those with black holes. And then ended up at Santa Cruz, sort of a whirlwind tour from not really knowing what I was doing to just very tripling down on STEM and going from opportunity to opportunity. And now in grad school, I basically focus on the most violent explosions in the universe, looking at black holes that merge with each other or neutron stars that merge with black holes. And those events in the universe create gravitational waves. They physically stretch space and time. And I'm sort of like a treasure hunter. I'm pointing telescopes looking for the optical afterglows and the optical light associated with these titanic collisions. And so it's been a wild ride to get here and to have these important results so early in my career. So I'm very thankful for the team that I've been working with. But then I also wanted to mention something about ARCS, about how important ARCS is supporting young scientists, but also supporting me personally. This last August, some of you may know that there was a large fire season in California. So I was actually one of the families, I live on campus, that was sort of dispossessed, like forced to flee from Santa Cruz. My wife, she was 9 months pregnant, and we had a little daughter. And this is the height of COVID. So we didn't know where we could go to deliver, where we could be safe from COVID. But I knew that May that I had won an ARCS fellowship. And so I knew that I had this ability to support myself and get through that time of, partially depending on the generosity of others, but also knowing that I was able to certainly take care of my family and get back to Santa Cruz as soon as I could because of the ARCS fellowship. And so that has been key. I feel so lucky to be able to weather that kind of impact to my own career, protect my family, but then still be able to turn back to the stars and look to what really inspires me and continuing to do that research. So it's a little bit about how I got here, this winding road, and hopefully the road ahead is a little bit more straight towards professional research.
Well, Dave, that winding road has really served you well, it seems. And what a wonderful story of how you got from history to now looking to the heavens and also getting through that very bad fire season. And we're glad that your ARCS award helped you. Your energy and passion are truly evident. And we may have time for a couple questions, but I know that Dr. Schloerb has one that we're going to start with.
Well, I think if you ask any scientist, you may not find quite as windy a road as Dave's, but you'll find these moments when people change direction and do things, and so I'm actually kind of curious how you wound up picking your thesis topic here. Right.
Yeah, it's a good story actually. When I started graduate school, I had big dreams to be a cosmologist, to study, the universe at the largest scales. And so because I was a part of a transient observing team, which is where we look for things that change in space on short time scales like supernovae, one way to do that is to measure type 1a supernovae. So I was going to be a supernova astronomer. And as a side project, my advisor had me think about, if there was a gravitational wave event, how would we look for the associated light? So that side project turned into something that consumed more and more of my time right before LIGO was gonna turn off for O3. So O3 stands for Observing Run 3. That's the observing run that ended in 2017, and it went on for a year. So I happened to be actually in Copenhagen at the Niels Bohr Institute, which is this amazing place, is the birthplace of quantum mechanics, right? It's sort of hallowed ground for a physicist. And I just happened to be at this seminar for gravitational waves. And then there was an alert. And back in those days in 2017, you had to actually sign a document saying that you wouldn't say anything, like you are talking about the Sagittarius A-star result that you have to sit on for now. But you could hear everyone's cell phone go off in the crowd listening to this talk, right? And everyone's looking down and seeing that there's a neutron star merger. So a neutron star is the core of a massive star after it undergoes a supernova. So two neutron stars merged together, and this alert was sort of like this golden alert, right? It was like the false alarm rate was like 1 in every 10,000 years. So everyone thought it was real. Everyone kind of got down to their command stations. And I had just been training for this, right? I had just been like practicing these protocols. And my boss, my advisor, was on a date. And I had to text him. I said, Ryan, there's a neutron star merger. We have to search for it. And he's like, yeah, right. If there was a neutron star merger, I'd know about it, and it'd be booming in the X-rays. And I'm sitting there. And so when I give talks on this, I actually show this text exchange I had where I was really just beseeching him to come back. So he comes back. We have a team in Chile. We have a team in Santa Cruz, and then the team in Copenhagen. And on our 9th image, using the algorithm that I had designed, on our 9th image, we took the very first image of an optical light source of a gravitational wave event, and so this was huge. And that's how I got into this field, was just sort of like being thrust into it by and honestly, it was all those years programming and banging my head against the wall and operating under pressure and these kinds of things, that all just these intangibles that I think you don't realize how important they are until they are. And so, yeah, so then we made that image. We have our own image, right? So
very good.
That is incredible. It is such an amazing story. And we're getting short on time, but there's one question here from Melanie Reber, if I say her last name right, and you touched on it just then. Do you think that having a humanities background and a diverse work history helped you to be successful as a scientist? And if so, in what way?
Without question. And almost on every dimension, actually. So, you know, in terms of, I mean, even reading the scientific literature, sometimes, you know, having to read Ulysses will help you try to break through some of the infinite walls of text that scientific papers have. But I mean, understanding the context that we live in, the, you know, the sort of intellectual context that we're in. So from that perspective, that part of academia helped, but also learning how to program, learning how to work on teams, learning. I used to be a programmer for an advertising agency, actually, and there would be these like seasonal rushes where, like, you know, Thanksgiving or Christmas, they'd want to publish these big web applications, these big experiences that customers wanted to have. Well, finding an optical counterpart to a gravitational wave source feels a lot like a New Year's Eve deploy on a consumer website, right? There's that intensity and that thinking on your feet that I think that's inside everyone, but certainly having the chance to practice it before you get into science helps. And so I'd say from a range of soft skills relating to people to the hard skills that you learn throughout all the things you do have definitely been part of what's made me, I think, survive grad school to this point, but also just be productive.
So that's fabulous. Well, you've been very productive, and we're looking forward to your completion of your doctorate and moving on in your career. And so thank you, Dave, for being here. And Dr. Schlerb, thank you for being here as well. It's just been marvelous having both of you. And we hope that all of you who have been here today with us will join us at our upcoming National Scholar Speaker Series. It's going to begin on August 24th at the tail end of summer. And then every other month, you'll have the opportunity to hear from 2 ARCS scholars from 2 different ARCS Foundation chapters. And in fact, we have a list of over 40 ARCS scholars who are eager to speak about their research. So we'll have no shortage of exciting content. The topics will range from medicine to artificial intelligence to the visual system of the octopus. And if you're curious about that, take a look at the award-winning film, My Octopus Teacher. It's fabulous. So right now, the slate of topics and speakers are in the process of being developed. So stay tuned for that. And please let us know if there's something of particular interest to you. Our goal for ARCS Forward is to be interactive and informative. And in order to get your valued feedback, which will help us to create and shape future content, you'll be receiving a short survey along with a link to today's recording, either for you to rewatch or for you to share with others. So thank you for attending today's inaugural session, and thank you to the ARCS Forward team who organized this entire series. And thank you, Sherry Lindeen, for being here as our fabulous leader at ARCS National. So we look forward to seeing you next time. Be sure to mark your calendars for August 24th at 5 p.m. Central Time. Now, meanwhile, stay safe and be well. Thank you.